Welcome to the AI Research Roundup. I am Alex, your host. Today is May 9th, 2025. Alright, we are looking at a research paper from Hugging Face's trending list, published 5 days ago, titled SkillMimic-V2, Learning Robust and Generalizable Interaction Skills from Sparse and Noisy Demonstrations. This paper addresses reinforcement learning from interaction demonstration, or RLID, how AI learns from imperfect examples. It uses a stitched trajectory graph, or STG, to link skills, a state transition field, or STF, for new connections, adaptive trajectory sampling, or ATS, for smarter learning, and historical encoding for memory-dependent skills. So, what does this look like in action? Well, this first figure gives us a great visual of how these techniques enable physically simulated robots to learn complex interaction skills. And they do this from what we call sparse demonstrations, meaning very few or incomplete examples. You can see robots learning to dribble a ball robustly, that is, reliably, even with slight disturbances. They also learn to generalize, which means applying skills to new situations, like grasping a book from various positions or reorienting a cube, all from minimal initial showings. This really demonstrates the system's ability to overcome the problem of imperfect training data. Building on that, this next diagram, figure 2, really zooms in on the core challenge when dealing with those imperfect demonstrations. We see what is called a reference trajectory, shown by the black dots and arrows, representing the initial, possibly flawed example data. It might even contain physically impossible steps. The goal, then, is to learn an ideal trajectory, that is, the yellow path, which is physically achievable and stays close, within what they call an epsilon neighborhood, or a small allowable area, around that original imperfect example. This visual nicely shows how the system aims to find better, feasible solutions. So how does the system actually find those better, feasible solutions? Well, this next figure lays out the core method. It begins with sparse demonstrations, say, separate examples of a shot and a dribble. The system then uses data augmentation. First, a stitched trajectory graph helps to identify potential ways these separate skills could link together. Building on that, a state transition field essentially fills in the gaps, establishing plausible connections even for states not explicitly shown. Then, using reinforcement learning from interaction demonstration for the training phase, a process made smarter by adaptive trajectory sampling, which prioritizes tricky parts, the AI learns these enriched interactions, achieving robust skills. Alright, so how well does this whole approach, which also includes a pre-trained history encoder for remembering past actions to better handle tasks needing temporal context, actually perform? Well, this table shows the quantitative results on ball play and basketball tasks. We see metrics like success rate, or senior, for task completion, epsilon neighborhood success rate, or epsilon NSR for robustness, and transition success rate, or TSR for switching skills. The SM plus hours row, that is SkillMimic-V2, achieves an average success rate near 97%, and its average transition success rate jumps to about 94%, up from just 15% with the original SkillMimic. Okay, moving beyond basketball, this next table presents a quantitative comparison on para-home, which is a set of household tasks. We are again looking at success rate and epsilon neighborhood success rate, but also at normalized reward, or NR, which basically measures how well the learned behavior matches an ideal behavior, with higher being better. Across various tasks like placepan and pour kettle, the SM plus Rs method, which is SkillMimic-V2, consistently achieves very high, often perfect, success rates. The average epsilon neighborhood success rate also shows a big jump, indicating strong generalization even in these everyday scenarios. To really understand what makes SkillMimic-V2 so effective on those basketball tasks, this table presents an ablation study. An ablation study is where researchers test their system by systematically adding or removing individual components to see exactly how much each one contributes. We can see the baseline SM has a success rate around 53%, but as they add in the stitched trajectory graph, the state transition field, adaptive trajectory sampling, and the history encoder, the success rate and transition success rate jump dramatically, with the full system achieving nearly 97 and 94% respectively. This demonstrates each element is vital. So as that ablation study clearly showed, each component is vital. In essence, SkillMimic-V2 tackles how I can learn complex skills from very limited and imperfect examples, a core challenge in reinforcement learning from interaction demonstration. It achieves remarkable robustness by using its stitched trajectory graph to find links between skills and its state transition field to fill in missing steps, complemented by smart training techniques like adaptive trajectory sampling and a history encoder. That is all for this AI Research Roundup. Thanks for tuning in, and see you next time.